Hi there. Hey, this is Clint Mason with Kaizen Well Solutions. I was going to throw a short little talk about critical rate and what that means to your well. And there's really only two key items that impact the critical rate from a 5,000 foot view, I guess. One is pressure, and one is the tubing size or the area inside that tubing. And in this graph here, I show and many people probably have seen this before, but basically this graph shows your tubing um, size. So here we have 1751 ID, 1995, which would be basically your 2 3/8. This would be your 2 7/8. This is 3.5, which is a 2992 ID, and 4.5, 3.958 ID. So roughly your case. A couple of things here. So this is pressure in kPa. Basically, 700 kPa is 100 psi. So at 100 psi or 200 psi or 1400 kPa, you can see that 2 3/8 tubing has a critical rate of about roughly 14 E3, which again is roughly about a half a million. It's probably closer to 420 MCF or something. And that same uh, flow rate in 2 7/8 tubing is this line here. So we go from 14 intersects and we can run this across, and it's probably around 20 E3 or say 650 uh, MCF a day. And then of course your 3.5, you're closer to a million standard cubic feet a day or 28.3. That's why I put that in there. And then in your 4.5, you're pretty close to almost 2 million a day. So at that same pressure, depending on the tubing size, it increases quite a bit. And also you can see as your pressure increases, critical rate also increases, or the rate, the amount of gas that you need to be producing in order to lift that liquid. Now, what is critical rate? I mean, critical rate is basically the gas moving at a velocity um, uh, quick enough that it's able to lift and push the liquid that is in that tubing. And I kind of think of it this way: is water or liquid that you're trying to lift is a whole bunch of basketballs, and the gas going by it is a whole bunch of hands. Now gravity is trying to pull those basketballs down, and gas going up is bumping into those basketballs trying to push them up. And if you're not bumping into those basketballs fast enough, gravity's going to win and slowly pull them down. And as they do that, they start to get larger and larger bubbles or uh, build up of fluid, and they start to fall and collect on the tubing walls and things like that. So that's generally how an easy way to think of critical rate. So when you're standing there by your wellhead and you're looking at this, looking at a wellhead, and you look at a well that has 100 psi or 50 psi on it, and in a certain size tubing, and the well's lifting liquid very effectively, and then you walk over to another well that's at 300 or 400 psi or 3,000 or 4,000 kPa, and it's starting to liquid load even though it's producing the same amount of gas. This is why, as your pressure increases, so does the required rate, because as pressure increases, basically the velocity of the gas drops. It compresses that gas more. There's also some other effects as the gas becomes denser because it's compressed. It actually doesn't need to move as fast, but there's kind of a crossover there anyways. So pressure increases, more rate is required in order to stay above critical rate. So basically, if you fall below critical rate, all that happens is your liquid starts to collect and it starts to build up in the tubing, and that's what you'll see. So let's go on to the next slide here. Now here's kind of some flow regimes. So if you have some basic ideas. So anywhere above this line, which is your slug annular transitional flow, is really considered to be above critical rate. So we start off with single phase dry gas. There's no liquid in it. Of course, it's going to be above critical rate because there's nothing in it that's collecting or falling. But most of our wells are in a mist flow where basically all the liquid coming in is being swept up in a continuous mist and carried to surface, and that's well above critical rate. Then you get into this annular mist flow. Now, my experience has been that from the calculated critical rates to standing at the wellhead and watching what's happening, they're not they're undervalued. So I would say by 15 to 20%. So if your critical rate, calculated critical rate was 1 million standard cubic feet, you'll start to see slugging and uh, some opportunity to optimize your well at probably closer to 1.1 or even 1.15. Um, as soon as you get below that, you're going to be able to start seeing some upside by doing some sort of optimization. This annular mist flow, what's happening is your gas is sweeping up the center. Of course, the center of the tube or the pipe is going to have a higher velocity. As you get closer to the wall, there's friction and things like that. And the gas kind of bullets out and starts to push the liquid towards the side. Now, this liquid is still coming to surface, and there's some great videos online that a person should take a look at, and you can actually see this liquid slowly working its way up the tubing, and that's still considered above critical. But at that point, I think you can gain from doing some sort of plunger lift or other optimization methods. Now, when we get to what's a critical rate, we move to slug annular transitional flow, and basically all this liquid that was building up on the side, now there's not enough flow through the center to support it and keep it pushed against the wall and moving up. It starts to fall down on itself. It's starting to collapse. So it's creating this liquid is pushing up, and then it falls in, and then gas blows through it, and then it falls in. So you have these continuous bumps, and when you're looking at your flow at surface, and if you had no Barton meter in there, you could just see that thing sitting there bounce, 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 and you'd hear it surface fluid slug in, slug in, slug in, kind of gas, slug in, and it'd be kind of bouncing continuously. Once you get past that point, we get into slug flow with liquid drawback. Um, Basically, when you're at this point, what's happening is you're getting a big tall column of fluid that gas is slowly trying to push through and bullets through. And as it's pushing through, it's pushing a lot of that liquid off to the side. And as it breaks out of that column of fluid, the majority of the fluid falls back down, and then the gas comes to surface. And of course, if you were looking at a chart or your SCADA, you would see these big spikes in gas, and then a drop off, and then it might sit near the very little flow, and then a big spike, and then very little flow, and that's pretty um, typical of slug flow with liquid drawback. And it's pretty interesting. Once you get these slugs of liquid falling, it's quite hard to stop them from falling and turn around. So you actually get this real buildup of energy that has to break through that liquid dropping, and then so you get a lot of these peaks and valleys. And finally, you get down into bubble flow, and bubble flow is basically you're just pushing a little bit of gas that's kind of bubbling through the liquid. Your well stops making liquid. I hear a lot of people say, "Oh, we don't have a liquid problem anymore because basically we stopped producing liquid 2 years ago." Well, it doesn't mean you don't have a liquid problem. It just means it's not coming to surface anymore. So uh, if you used to produce fluid and now you don't produce fluid, it probably doesn't mean you stop producing fluid. It just means you stop lifting it to surface. Probably have a really good optimization opportunity there. So let's go on to the next slide here. So another interesting thing is that you can see where, and I've seen this a lot in gas wells with water, especially production, where you can be slugging in the bottom areas of the tubing in some of the deeper wells, and you can you have a hard time getting liquid all the way to surface, so you'll be slugging and carrying on. And of course, as that slugs in there, it starts to liquid load when you get more and more weight pushing back on your formation, the rates start to drop, and then it slowly builds up and you'll die. Even though when you look at surface, you might say, well, my surface flow rate should be above critical, but when you look at your casing pressure and you kind of calculate it back, you say, oh, geez, well, actually somewhere between my end of tubing and my surface, I'm actually into my critical rate or below my critical rate. So it's creating some interesting dynamics in the way the liquid is moving. When you're looking at critical rate, you have to consider the entire well bore. not just your surface pressure. You have to understand what's going on downhole as well. Here's kind of a representation of what that means. So if we're in mist flow and we were to weigh, that column, it might be 0.3 kPa per meter. When we get to that annular mist flow, we might have 1 kPa per meter. Slug annular transitional flow, 3.6 kPa per meter. Slug flow, might be 4.6 or higher. Bubble flow, we're probably 6, 5.5 to 7 kPa per meter. If you looked at just basically dead liquid that was sitting there, it's about 10 kPa per meter is what it would be pushing down on your formation. So basically, when we're in mist flow, we have we're lifting all that fluid, we're carrying it in a nice, um, misted fashion. Your end of tubing pressure is going to be much lower, and this is basically why, as your well loads up, you can see the pressure go up because the column weight increases, forcing that formation pressure or the area near the end of tubing has to start to build up, and eventually that column weight will overcome the pressure you have in your formation, or could, and then the well stops flowing. So that's there. So here's what's the effect of falling below critical rate? Well, it's pretty simple to see, and we've all seen it, where basically as the well loads up, production drops and the well eventually stops producing, and we have to intervene, whether it's swabbing or some form of optimization like plunger lift. So basically what I'm showing here is this is just a made up graph that I put on here for representing what an IPR is. And basically, as that liquid starts to collect in the tubing, you saw that the pressure here, or on the casing, you can see it starts to climb. Well, as that pressure climbs, we can take this IPR, or inflow performance relationship graph, for example, in this pretend well, and we can draw across from the current pressure, and we intersect this line, and then we go straight down, and we say, oh, at this particular pressure, um, we have the ability to produce about 20 E3 of gas. But if I was to go in there and we did some sort of intervention, we put a plunger lift in, I get this plunger running, it goes through, it sweeps that fluid out that's accumulating. It allows that pressure in this area or on the tubing to decrease. And then pressure starts to drop, get down to 2,000 kPa in this case, and we run it across and we intersect this curve, and we went from 20 E3 to 28 E3, or about 250 MCF a day increase by removing fluid in this example of the well. So everything that we do now, critical rate is a number. It's not an exact number. Different weights of fluids and all that. Of course, that affects all of it. But it gives you kind of a good idea when you're looking at a well and you're starting to see your casing pressure increase and your production drop. It's good to have that understanding what critical rate is. First of all, is it liquid loading, or could it be buildup of paraffin, a hydrate? It could be lots of different things possibly in your well. And if you're flowing, if you can take a look at it and say, geez, I'm flowing, 2 million a day in this well at 150 psi and 2 3/8 tubing, well, the chances of it being liquid loading as the problem is probably pretty low. But it at least lets you know, if it's not liquid loading, then yeah, maybe it is paraffin. We see lots of wells where we get that paraffin buildup, free flowing wells, or even if you have gas lift, and it really starts to build up, and it really starts to put a lot of extra pressure on the back pressure on the well. So just being able to identify the difference between liquid loading and some sort of interference like paraffin buildup could save you a bunch of time. But basically, anytime we can reduce that pressure down here on the formation, whether it's removing liquid, removing buildup, opening up chokes at surface, any of that stuff is going to have the same effect on this curve. So if this pressure drops and around this formation and the tubing in this example, if I can drop that pressure, I'm going to be able to increase production. So anyways, that's kind of a quick review or conversation about critical rate. It's really just aimed at, field people to give them some tools when they're standing by the wellhead trying to understand what's happening. Very, very basic. There's of course, very in-depth calculations and all sorts of time you can spend figuring this out to the nth degree, but it's really not required when you're just trying to understand the mechanics of your well and make it operate. You just need some basic idea where to start looking. So hopefully you've enjoyed this. There's been a little bit of information, and yeah, everyone have a safe and enjoyable time at work. Take care.